All right, here we go. So as you can see in this drawing task, it's basically if you are looking at it as a TV, and this is your point of view, and you're looking through the TV and looking at a three-dimensional space, we can actually draw these vectors in 3 dimensions as our X, Y, Z. So if there was a three-dimensional plane, basically connecting each point of this cube to where you're looking at. We take each one of these vectors. Remember, it just gives us distance and direction. We'll pretend we're really good drawers as we get a little bit closer. So each one of these 3D, one more time. Oh, this is that like Mobi device thing I was talking about. Yeah. So I can actually walk around just as hard to walk around. That's why I really want that invisible thing. Yeah. I actually have one for each person that works here. So when you get here, you'll get one as well. I know my Algebra 1 teacher does. I don't know if the others do. It really just depends on how familiar with you are. The issue is a lot of them have an issue finding the pin on it. I find it to be easier to use a Zoom call because the Zoom call gives you that pin look right there. If you just try to be like on a PowerPoint or any other type of documentation, finding the dot somewhere on the screen is kind of hard. You almost have to make some marks to kind of find you out. But the Zoom has the little pin icon, which then I can find myself anywhere. I don't know. Preference, I guess. I started my teaching with a Mobi, which was yeah, that's why I'm in Zoom. Plus, I also record for anyone that's absent, and then I post it on Google Classroom for them. You'll find out in a small town district if they're involved in one thing, they're involved in about 20 things. But hold the expectation. All right. So there is basically all these different vectors that we can basically draw out and it will build a three-dimensional shape. So we can take it and we can go in reverse as that as well. All right. So any major questions on that? So basically what we're going to be doing is figuring out and calculating these vectors and then how we can build these vectors to then build some type of three-dimensional vertices. Okay, so there's zero numbers currently. We'll put this in space, and if we call this the origin, and we say that this object from here to here is, the X is 20, the Y is 30, and then the Z could be like 12 or something like that. There's a way that we can use our time, and we can calculate the time if this object is consistently moving, calculate what the T is, find out what the X and Y could possibly be on a two-dimensional space at the exact same time. It'll give you more information than this. This is just blank right now, but it will say, hey, this and this for the three-dimensional places where it's located. Then we can use time to go, all right, in 1 second it'll be here, 2 seconds will be here. Now, what would this look like on a two-dimensional plane if we take the Z-axis out? That's kind of what you'll see here on this next part. But the visual aid, this is basically, again, if you want to really see this, that ALICE program, again, that's ALICE. And if you Google 3.1 with it, it'll pull up, I think it's on the version of 3.9. It's literally just a program of you just making three-dimensional shapes. And you have like a little dot here and a TV screen. And it kind of explains how these 3D images can become 2D images for us. Again, I played with it and still didn't know how to teach it to y'all. So that would be more of a concept that y'all can play with if y'all are interested. If we had more time on our hands, I would have gave you a day to play with it, but we don't have that kind of time. All right. Any other questions though? All right, let's look at the math part of it then. So when we look at this first exercise here, or example, so you're given a three-dimensional objects are projected onto screens with a finite dimension. If often limits the field of view, which is just labeled as FOV, or the angle the screen represents. So the limiting effect can vary based on the size of the screen and position of the observer, depending on what angle you're looking at. we visually see it differently. We'll pretend that that person was directly in the middle of the screen, but you could be on the right or the left, and we would see, well, the vectors that help us see it would be different for our location. Part A just wants us to sketch a diagram that would be used to calculate a viewer's field of view representing theta in relation to the horizontal width of the screen W and the distance the viewer is from the screen D. What we're basically doing is we're going to develop an equation. So as y'all say, I gatekeep the equations. That's what I'm going to do until we develop the equation. So here we go. So this is what we're going to try to do. So here is a TV screen. And we're going to pretend that's a perfect parallelogram. It can be a perfect rectangle too, if you'd like. All right. You are sitting currently right here. That's your point of view. That's your eyeball. Let's make this even cooler. Let's draw an eyeball. Some of y'all artists out there are like, that's a horrible eyeball. All right, but there's your eyeball. That's your point of view or your field of vision. This right here, again, we're going to pretend that's a straight line. It's going to be the width of our viewpoint. All right, so that is your screen width. From the eyeball to the screen, or the center of the screen, would represent the distance. So that would be the distance from the screen to your eyeball. And then you also, so that's the center, but your field of view ranges from how wide this the screen is. So you're seeing everything from left to right at every point of view. Your vision just might be different. This angle right here, given depending on how close or how far you are, that will be our theta. Right? So there's our distance to the screen. You have the width of the screen, and then from your eyeball, we have a degree depending on how far or close you are. Obviously, the closer you are, the wider the screen. And the further you are, the smaller the angle of the measure. All right. Any questions on that? So that's just where these things are labeled. Part B there, and what I'll do is I'll write part B up here so we can keep our image up there together. This would be an angle bisector from geometry because it's from the center of the screen to the point of view, or the FOV, the focal point, or where you're looking at. Yeah, so each one of these would be theta divided by 2 altogether, giving you the theta. Yes. All right, so again, I'm going to write B here. You can write B where B goes. All right, so this part then says, assume that the person is sitting directly in front of the television screen, whose width is 48 inches. So the TV screen is 48, so that would be your W. At a distance of 8 feet, so there's your D. You're going to use the diagram and the right triangle trigonometry to find the viewer's horizontal view for theta. Now remember, the way we do this for our angle, how do we calculate theta or the angle? Perfect. Yes. Yes. Go ahead. Ask a question. Yes. Hold that thought. So I was just about to get that. We need to convert that either both in feet or both in inches. What's the easiest for y'all? I agree. So 48 inches would be 4 feet. Unless the thing tells us to keep it in feet or inches, it really doesn't matter which direction you go. If I wanted to put the 8 feet in inches, just multiply it by 12, and was that 96? So 96 inches. Either way works for me. But I do agree. I think feet might be a little bit easier to tell. So to find our theta, that would basically be very good. Issue is we need to determine our B and our A, in which theta we are looking for. So in this case, as Mr. Hallam said, this right here, his whole thing is theta. This right here would be then theta divided by 2. Because this right here would be directly in the center of your view, and then you would have each endpoint of the vector. So therefore, if I wanted to find just one given angle of this vector, knowing that this is 4 and that this is 8. Sorry, not that one. This one is 8. Hmm? Well, the angle that you're looking at. So again, the closer you are, the wider that angle is going to be. The further you are, the less that angle is going to be. So depending on where we're at, that's kind of how things are changing. Now, this entire width of the screen is also 4 feet. So what would half of the screen be? All right, so here we go. So now when we kind of build this up, we kind of see what do we got going on here. We have a triangle, right? Not necessarily, we don't know if it's a 90-degree triangle, but to find this measurement out for our angle, we're looking for this guy right here. All right. So we could do the whole square root of a squared plus b squared to calculate what that angle would be. But I mean, not the angle, the side or the distance from this side of the screen to your eyeball here. But since we're looking for the theta, this again would be the theta divided by 2. So for our tan inverse, that is the theta we're looking for, or currently can be able to find. Your B and your A are these guys right here, just like we've been doing with our regular vectors. Because again, this is the vector that we are looking at. So when we do this, this will give you theta divided by 2, and then tan inverse of B over A. Now, which one's your B and which one's your A? It will matter. What's your change in your Y and what's your change in your X? Okay. Hmm. It should be your A. Yeah. So that's how we got to the distance for the square root of A squared plus B squared. No, we don't use the SOHCAHTOA right now. We're using the vector part of it. So which will give you the tan inverse of B over A, which is where the SOHCAHTOA would come from for the opposite over the angle or opposite over adjacent. That's how we get the B over A formula. That's where we started. I don't know, 27 lessons ago. Hmm. If we go in this direction, we assume that this is the X, and this would be the Y. Hmm. All right, so let's go with that. So if we go by 8 divided by 2, so that would be your change in Y over your change in X. That would be the tan inverse of 4, pretty much. That's what I was debating. Because I don't think this would be your X. I think this would be your Y. Yes. So the opposite of theta, adjacent. That's it. So we're a theta here. Again, with SOHCAHTOA, this would be the opposite, adjacent, and hypotenuse. So this would be the change in your Y over your change in your X, depending on the angle that we're looking at. So almost want to draw this on a plane here. Correct. In this situation, we want this angle. Yeah. So that would be your change in your Y would be the 2, and the change in the X would be the 8, using the dimensions here. Trying to take this, well, we're kind of looking at it from above to a side view. There we go. So yeah, I agree. So your X again would be the 2 would be on the bottom, and then your B would be the A. Ah, dang, that's right. No. So we're looking at it in this point of view. You're kind of looking at it at an angle from above. So you got someone that's staring at the screen, and then we're staring at them. If you look at it from a side view on an XY plane on that we're used to, this is where your screen is. So you're 8 feet from the screen, and then you're looking basically, if we turn the screen sideways, 2 feet above. So your rise is still 2. So this is still going to be rise over run. It's just this point of view makes it a little bit harder to see because we're not looking at it on our XY coordinate plane. So if I go here, this would go over 8, change to 2. So it's still rise over run. So nothing's been contradicted. It's just the visual aid of this looks like we're looking at it from this point. But in reality, if we flip it up, then you can see that this is 8 and then this would be 2. So your change in your X is 8 and your change in Y is still 2. So your B would still be 2 and your A would be 8, which gives you the 2 8s here, which will be 1/4. I like the way you see that. Yeah. In this situation, if you're given the situation again, but not every situation would be the same, as we've seen in most of our word problems. So then we can calculate what is the tan inverse of 1/4. 14.03. Again, make sure you're in degree mode in your calculator. If you're getting like a really long decimal, you don't want to put in that one because that'd be the radians. All right, now that's what theta divided by 2 would be, since that's what this was given. What can I now do to find theta? Just multiply both sides by 2. So our full theta would be what? There you go. So now we found our theta being 8 feet away at a 4 foot widescreen TV. Basically give you that full value right there. All right, so again, when we were visually looking at this, we're looking at it kind of like think of it like this. Here's my point of view. This is the way we were looking at it. But if we flip it and we put it more on an XY table so we can see it, the visual of this moving at 8 and this coming at 2 can now be seen that this would be the change in X and this would be the change in Y. So this would have been 8 and 2. That was the issue because I was looking at it as well with you. I was like, okay, well, if we assume that's the change in X, then this would be the change in Y. But if we look at it more at a 2-dimensional space rather than trying to do a 3-dimensional space here, then we can kind of see it a little bit better. But you could also use Jacob's concept of the middle distance will be your change in Y and half the screen will be the change in X. All right, now with that, we can also calculate what this distance is. And how can we calculate this distance? All right, so this is part C. I'm trying to keep it all together. Yes, this is there's a lunch and a B lunch. So we go to B lunch, so they just finished with A lunch. All right, so this is C again. You can put C with C. Now in this one here, what is my distance formula? Assuming that this would be the origin, how would I calculate? Okay, so that would be 8 squared plus 2 squared. So again, we'll be finding this guy's distance. So square root of 60, square root of 8 squared is? And then 2 squared is 4, and then 64 plus 4 is, and then the square root of 68 would give you, it can't be, but you can type in the calculator so we can get a measurement. Yes. There we go. And again, we are in feet. So this would be 8.24 feet for the distance here. So that would be how far would a viewer need to, oh, my bad. I didn't read that. I just read distance on part C. Part C is a whole different question. So that would be the, oh, what's the third digit? I was taking, you're so confident with the answer. 5 feet. All right, so that would be the distance here and the distance here as well. Now, that wasn't actually what part C asked. I just assumed that's what it was going to ask. But it says, how far would a viewer need to be from the middle of a computer screen with a width of 15 inches and produce the same field of view as the person in front of the television? So you could say this was part C, but we didn't actually care about the distance. So let me move down to part C. So we're going to go backwards from what the information was just given to us. And then what we would need to get to figure out that distance, right? That the change in y. So we'd be looking for the b. So again, using the formula tan inverse theta equals b over 2. Ah, man. B over a. What am I doing? Theta equals tan inverse. Yeah. That c that I just did wasn't part of c. I just assumed that's what it's going to ask, was the distance there. All right, so the information we're given is how far would a viewer need to be from the middle of a computer screen with a width of 15 inches. So now I need to convert this into feet. Why would I have to convert this into feet? Because that's what I did above. If I had kept it in inches, I could keep this one in inches. So what would 15 inches be in feet? It is 1. Okay, what is 3/12? 1/4 is what as a decimal? Good. So this would be 1.25 feet. You're more than welcome to keep it as a mixed fraction of 1 1/4. It's a little bit easier just to deal with the decimal part. All right, so there we go. So that is my new B, because that's the difference there, to produce the same field as the person in front of the television screen. Okay, so now the issue is on the television screen, this whole thing was 1.25. Now I want to have that same view. So if this whole thing is 1.25, what would this part be? Okay, so there is my B, and then we're trying to figure out how far do I need to be from this computer screen. Oh, perfect. That's what I'm getting to. So I know my theta. What was the angle that we calculated on part A? Was it 28 or something? I'm gonna. Oh, that would be 1.5. So confident again. All right, what is it, guys? 0.625. That sounds a lot better. All right, we good? So on the previous one, we actually had to use this for the theta divided by 2. So whoever just asked that question was a great question, because this was my theta divided by 2 that I'm going to have to use. Who asked that a while ago? Someone said we have to do it by halves because we're doing this measurement right there. So yeah, so that would be that's what we have to do. So we have to use this part of the formula that we used earlier, but now we know what was the theta that we calculated from part 1. 28.06 divided by 2 gives me the tan inverse of my B, which I don't know, over my A, which in this case would be 0.625. Did that? Yes. You could, yes. That's what it is. Okay, so change in Y with a 0.625 divided by A. A is what we're looking for, the change in X. Man, this three-dimensional stuff. No, it was on top. It was 2 eighths to give us the 1/4. Yeah. So again, if we flip this back over, then we see that this is the y-axis and the x-axis. All right. Okay. So in this case, yeah, we could just go straight to 14.03. I was just plugging into the equation that we started with in number 1. Now, when we first got this answer of tangent of inverse way back when, it's because we were solving for theta, so we were trying to get rid of tangent. This time, we're trying to get rid of tan inverse, so you can actually go the same direction and just figure out what the regular tan of this guy is. You just got to figure out what tan of 14.03 is of 0.625 over A. So basically what I'm doing there is I would take the tan, and that's what would cancel. That's how we end up getting the tan inverse formula. So what is the tan of 14.03? I did. Okay. So when we first talked about theta, it started off like this. It was tan theta and then B over A. And then to find it, we just discovered, well, if we just take the tan inverse of B over A, we will basically, what you're mathematically doing there is you're taking the inverse of both sides. So that would cancel. Now, in this situation, I'm not looking for theta. I'm actually looking for something inside it. So I actually want to go backtrack and take the tangent back over there. So instead of taking the tan inverse, I'm now going to take the tan of both sides. So now that I got rid of the inverse because I'm trying to solve for that missing unknown. It's like taking the opposite of a square or square root, right? You're trying to get rid of the opposite operation. Go ahead. Ooh, I like that. So we could have taken, so that's what we're actually probably going to calculate. What is tan inverse, or sorry, just tan of 14.03? Go ahead. It's going to give you probably 0.25 because she makes a good point that pretty much what's inside, we already know what's inside the tan inverse has to equal 1/4 to get the same angle. No, that's a great point. So let's do that. So when you type in tan of 14.03, what did we end up getting? 0.25. All right. So let's take that. So that's 0.25, right? Not 05, 0.25. Okay. Which will be that 1/4 we started with, which obviously for this to be the same angle, this would need to be the same ratio. Now you're asking, how do we get that number? How do we get a from the bottom of a fraction to solve it? I have to multiply by a. So now if I multiply both sides by a, the a over here would go away, and now I have a times 0.25. That's a times there, a 0.625. Now what would you do to solve? Divide. So that is how you get that second number. So 0.25 goes into 0.625 how many times? At least 2 point something. 2.5. So you need to be 2.5 feet from the computer screen to have the same angle that you are from the TV screen. Go ahead, ask the question, absorb it, and then ask the question. Well, basically, we kind of did. I get the formula. We based it off of this one. The only thing we changed was that theta divided by 2 because we halved the angle there. Other than that, it's been pretty much the same thing. Go ahead. What do you mean? Okay. So, okay. So to do that, bless you. Uh, if we use this entire angle here, man, that's, I wonder if you could, you have to figure out what that result would be because you would have to find your angle, which would be this right here. This would be the vector. And then I don't know. Hold on. So if we use the entire length, to find this guy right here. So what is tan inverse of let's go back earlier to what was the width earlier? 4. 4 divided by 2, which would be half. What's the tan inverse of 0.5? And we got 28. So there's a reason why it doesn't work, because we just did it and we got 2 degrees off, which can make a big difference. But why is the question? Yeah, so she was saying, why do we have to cut it in half? So if we did that, we would say theta is theta, and we would keep it as the width would be 4. So instead of 8 divided by 2, it becomes 8 divided by 4. So that's 0.5. But tan inverse of 0.5. So earlier we had to half it, right? So we got 2. So if the whole width of the TV screen was 4 feet, we halved it to 2 feet. And then we had the distance that we were from the TV. So that would be 8 feet divided by 2 feet. Oh, wait, sorry, 2 feet divided by 8 feet, which gave us the 0.25. Tan inverse of that gave us the 14 degrees or whatever. And then we had to times it by 2 to get the 28 to get the full angle. She asked, why can we not just use regular angle and then not half the width? Well, that was a good question, which made sense. So we just did that. So we did tan inverse of now 4 divided by 8. If we didn't half it at all, and then we should get the actual theta. Well, when they did that, you just got 26 degrees. So we're off by 2 degrees, and 2 degrees can make a big difference. So maybe, and that, you know what? I like that. That's probably exactly the reason why, because I could technically use this angle here, but I would again just be looking for this theta divided by, oh man, that's why I used the thing went for it. Hold on. This would be the theta divided by 2 over here as well, because you'd be calculating this distance if you did that point, but you'd still be doing by 2, and then this would still be 0.625 as well, or the 2 on each side. Because of this guy, because it'd be different if it said the angle distance from my point of view to the edge of the TV was 8 feet. Now I can just treat it as theta and the full width. But because I'm telling you the distance to the center of the TV is 8, I can't do the same thing, because now I can only calculate the half angles in between and then double it to find that full angle. So if it would have said, as I'm standing here, I'm 8 feet from my eyes are 8 feet from the edge of the TV. Now I can just do theta is equal to 10 b divided by a, and I don't have to change anything, because I can see, all right, this distance, and that will be the change, that will be the change, and I'm still calculating, or in this case, I'd be calculating this vector right here. But because the vector that we're looking at is the halfway between, I can only calculate half of the angle and then double it to find the full angle. But that's a very good question, because logically that almost makes sense, right? Why, if we're going to half it twice, why don't we just not half it and then give you an answer? Yes, sir. Absolutely. The names of them, yeah. Very good. More like probably like a acute or a most likely probably a acute chart. Yeah. Yep. Yep. Very good. And that's why we were able to use the tan inverse of the B over A, is because of the opposite over adjacent type stuff. Any other good questions like that? Yes. Because then it would no longer be theta divided by 2 anymore. We would have to figure out what that ratio would be to figure out how skewed we are. I doubt it, because we're objective right now. It's just to find the projection. But I wouldn't put it past it. That's probably more like your college type stuff. No, 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 no. It'll be straightforward. Any other questions? Yes. That's what Layla just asked. If we're skewed a little to the right, we cannot assume that they're both divided by 2. We would actually have to know what the ratio is. Like if it was skewed a third to the right, then we can say this is 1/3, this is 2/3 of it. Then calculate it that way. But we would need to know how much skew. We can't just say, all right, the guy's slightly over here. How much is that? Or if he goes maybe 8 inches, then we have to do a little bit more math to figure out the distance that changed and figure out the ratio of movement. Yes. Like directly a 90-degree angle. If you're told that, then it'd be already a right triangle. Well, the degree would be 0 degree. Oh, I guess if you're looking at the center, you're looking at from here. Yeah, you would just use theta. But then still half of the width though, because again, you'd be looking at to the center of the TV screen. But the theta would be just theta. It wouldn't be half a theta no more. Yeah, yeah. So that's what I just said. Yeah. So that's our TV. That's our TV, right? Let's say we're perfectly 90 degrees and we're looking at the center of the TV, right? You're trying to figure out this angle here. If you know that you are exactly, I don't know, hypothetically, say 8 feet, we know this is 4 feet, but this would still be 2 feet. Since you're looking for that one, I don't have to half the angle anymore. If I know I'm perfectly lined up with the edge of the TV, because this will give me my theta that I need. Oh, you're talking about, okay, well then if you're looking at the full angle, now it's back to half an angle because now you're here and you're looking for this guy. But it's not. This, it has a 90 degree right here. You have, so instead of 4 though, you would go back. I mean, instead of 4, 2, you go back to 4 because you're changing your X, you're changing Y. It'd still be A4, it'd still be a right triangle. But then now instead of the halves, you just go back to a full theta.
Yeah, but like if you're
Yeah, yeah. So that's what I'm saying. So this wouldn't be half anymore because they're not proportional. It's not a bisector anymore. So this would be like theta 1. This would be like theta 2, but total, they'll all add. How to find that one? Oh, that's if you wanted that theta. Okay, we could probably do this. We could probably take this and this, figure out what this unknown is. And then this would be unknown in 2. And then we haven't, but then you could use what we call law of cosine. So law of cosine goes a squared plus b squared minus 2 times a times b times cosine of c. That would be your cosine that you're looking for. There's a spot that we were going to cover, but we're just not going to make it. But this would be that formula to calculate it. And actually, when we were looking at vectors with the airplane and stuff like that, and the movement of the wind, we could have used this formula. Remember, I said there's a quicker way to do this, but they're assuming that you already learned this in geometry, and then we know our geometry background already. So there's just some spots that y'all just missed. All right, is the bell about to ring? Yeah, we're about 30 seconds.